After forming this equation, the inversion of A will be an A1, A2, A3. The B matrix will be an 1, 0, 0, 0, 0, 1, 0, 0, minus 3L square, minus 2L, 3L square, minus 1L. And then 2L cube, 1L square, minus 2L cube, 1L square, W1 theta 1, W2 theta 2. For essential, the strain displacement relationship, we have a previously sourced that the displacement at any point on element is given in the terms of assumed displacement function. So based on the displacement functions, we can calculate the coefficient matrix to obtain the nodal displacements. So for that, ux equal to fxy A inverse of ue. The above equation gives the displacement at any point on the element in terms of nodal displacement. Now the strain at any point within the element may be obtained from the chosen the displacement function. By differential, the examined for n differential depends upon the types of conditions. Here we are considering as an strain displacement functions. So here introducing the strain for finding the displacement equations. So it will be considered about the depends on the coordinate systems. So already we have seen displacement and then degrees of freedom, coordinate system, number of nodes, number of elements, types of elements. So here based on the coordinate systems, we can find the stiffness matrix. For a plane elastic problem, the strain is given by a first derivative of displacements. Here we are considering plane strain conditions. So strain equal to displacement by distance. So for that, E of x, E of y, gamma xy. So here consideration two plane, x and y plane. So for that, normal strain about x direction, normal strain about y direction, and CS strain for x and y direction. So normal strain about x direction, we are consideration dou u by dou x. Normal strain for y direction, dou v by dou y. CS strain for xy, dou u by dou y plus dou v by dou x. For a fractional problem, the strains are assumed with an curvature of the element and gives the second derivative of displacements. So here showing a secondary conditions. So primary conditions, strain about x direction means the displacement about x direction with respect to the length. If we considering of a secondary coordinate systems, the strain will be in negative manner. The displacements will be dou square w by dou x square for an opposite directions. For this, the beam have an thickness of t, and then load is acting with respect to center point to some other z deviations. The taking of small cross section of dx. For applying a loads, the deformations will be occur for a different angle and then different deformations. So the deformation will be considered as w, and then slope will be occurs based on the w, the initial point to final point. It will move forward u of x, that will be called as an theta. So here strain equal to minus z d square w by dx square. We want to derivative as usual. So dw by dx equal to 0 a2 plus 2 a3x plus 3 a4x square. Again we want to derivative d square w by dx square 0 0 2 a3 plus 6 a4x. So strain equal to minus z 0 0 2 6x a1 a2 a3 a4. So here we take it as an a1 a2 a3 a4 a1 0 a2 0 a3 2 a4 6x. So that will be mentioned here, and then minus z. So strain equal to general strain equal to minus z. The 0 2 0 2 6x will be considered as g, and then the unknown will be considered as a. So strain equal to minus z g a transverse u. The a will be considered as a transverse into displacement. Already we see in the previous slides. So the strain will be considered as an minus z g a inverse of u. Here z is ignored since we are considering the beam as unit thickness. So if we consider as an unit thickness, so for that we are neglecting the z value. Then proceeding is generaling. Hence, if z is assumed to be unit, then the value will be replaced as an z is equal to 1. So for that minus 1, the g value will be 0, 0, 2, 6x, and then b value will be 1, 0, 0, 0, 0, 1, 0, 0, minus 3l square, minus 2l, 3l square, minus 1l, 2l cube, 1l square, minus 2l cube, 1l square. And then the displacement value will be w1 theta 2, w2, sorry, w1 theta 1, w2 theta 2. So this is the general form. Already we know G term and then B term. Now formatting the equations based on the total potential energy equation. So this is the general form of equation. So potential energy equal to of derivative of strain transverse d strain dv minus force vector into displacement vector. Here E will be consideration UBG. So U transverse, B transverse, G transverse minus 1. The Z will be consideration 1. So minus 1. Then D. Again they're having a strain. So minus 1 GBU. And then with respect to the x direction, so dx minus force into displacement. For a beam, the D will be consideration EI, because the beam will be considering based on the material behavior of Young's modulus and then cross section of I. So here the D will be implementing a version E of I. So the D will be EI. So of EI, U transverse, B transverse. We will take this as common value. Integral of limit. So we will take it as 0 to L. So for that the limit of 0 to L, GT into G dx value. And then B UE minus F into UE. So this is the final general equations. Based on this, the minimizing the total potential energy equation, the equation is to be 0. So minimizing the equations. So for that, what we are going to do means dou pi by dou u equal to of EI B transverse integral of 0 to L GT G dx B into 2EE minus F transverse equal to 0. So this is the potential equations. So finally we are equated into a 0 form. So for that we will get this final potential energy equation. So for that equation we will equate into a 0. So EI, so EI BT, so that EI BT integral of 0 to L GTG dx, that U will be 2U will be consideration UE and then B equal to FE. So this is the final form. Here we are consideration stiffness matrix K, displacement UE equal to force vector. So the U will be in displacement and then F will be in force vector. The remaining term will be consideration stiffness. So EI B transverse integral of 0 to L GT G dx into B. So here GT into G. So GT 0026x, G 0026x. So first we want to multiply by 0, 0, 0, 0, 0. Again second 0, multiplying with this equation 0, 0, 0, 0. Then multiply by 2, 0, 0, 2 into 2, 4, 2 into 6x, 12x. Again 6x into 0, 6x into 0, 6x into 2, 12x, 6x into 6, 36 x square. So this is the multiple equations. After getting the gt value, now we want to integral the g transfer g value with respect to the limit of 0 to L based on the dx. So for that, the first values will be 0, 0, 0, 0, and then second value also will be 0, 0, 0. Then the 0, 0, the 3, 3 value will be in 4 dx. So here we want to place as an integral of 0 to L 4 dx, and then 3, 4 value will be in 12x dx. Here also we want to place a limit of 0 to L, then 0, 0, 3, 4. So 4, 3 will be in 12x dx, integral of 0 to L, 4, 4, 36 x square dx, integral of 0 to L. So here, if you want to do the integral, then we will get as an matrix of 0, 0, 0, 0, and then 0, 0, 0, 0, 0, 0. The 3, 3 value will be in, the dx will be x. So 4 x integral of 0 to L, sorry, limit of 0 to L, and then 12 x will be converted into x square divided by 2, limit of 0 to L, then 0, 0, 4, 3, 12, the x will be converted into x square divided by 2, limit of L 0, and then 4, 4, 36, the x square will be converted into x cube divided by 3, limit of L to 0. We are applying the limit values. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 4x limit we are applying as an L. So 4L minus 4 into 0. So 4L minus 0, 4L. Next, 12 L square divided by 2 minus 12 0 square divided by 2. So 12 L square divided by 2 minus 0, 6 L square. So 6 L square. Then 0, 0, 4, 3, 12 L square divided by 2 minus 12 0 square divided by 2. So that value will be 0. So 12 L square divided by 2 is equal to 6 L square. So 6 L square. And then 4, 4. 36 L cube divided by 3 minus 36 0 square 0 cube divided by 3. So 0, 36 L cube divided by 3. That will be 12 L cube. So final matrix will be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 4L 6L square. And then 0, 0, 6L square 12L cube. So K equal to EI B transfers the integral of 0 to L GT dx B. So already we know the integral of 0 to L BT GT G dx value. We know the B values. So after multiplying this equation, we get as a final stiffness matrix. So we know E equal to 1 0 minus 3L square 2L cube 0 1 minus 2L L square 0 0 3L square minus 2L cube 0 0 minus 1L 1L square. So this is the B transverse value. Integral of 0 to L GTG dx value will be 0 0 0 0 0 0 0 0 0 0 4L 6L square 0 0 6L square 12L cube. And then B value 1 0 0 0 0 1 0 0 minus 3L square minus 2L 3L square minus 1L 2L cube 1L square minus 2L cube 1L square. So here we want to multiply these three equations. So this is the 4 cross 4 into 4 cross 4, we'll get as an 4 cross 4. Then 4 cross 4 into 4 cross 4, we'll get as an 4 cross 4. So final matrix will be an 12 6L minus 12 6L 6L 4L square minus 6L 2L square minus 12 minus 6L 12 minus 6L 6L 2L square minus 6L 4L square. For all these things, the denomination will be L3, sorry, L cube. That will be taken it as an commonly outside. So final matrix will be EI divided by L cube into the particular matrix. where E equal to Young's modulus, I equal to moment of inertia, and then length L equal to length of the elements. So this is the final stiffness matrix for an beam elements. Thank you.